Hi everyone. So this is regarding this video. This lecture is regarding a question that I posed on LinkedIn. So this is a problem that I encountered some time back. I don't remember when, um, in a PLL-based circuit. So I thought I'll share it with you guys. It had some interesting results related to negative feedback. Okay, so I thought I'll share it with you guys. It's a very simple circuit. You have a current In of S with an output resistance Rn. So in this problem, Rn is equal to R, is AC coupled and fed to an op-amp based circuit that looks like this. Okay, it has some input impedance network, some impedance network in the feedback in an inverting amplifier mode. Now we are used to analyzing op-amps and inverting configurations, but the only difference here is the network looks a bit complicated. So in negative feed, the feedback path, you have a T network. So since input is current, output is voltage, it's a transimpedance amplifier. So in this question, because of this T network, we'll see some interesting results. So which is why I wanted to discuss this in the first place. You are supposed to find out the DC output voltage. Okay. Just to, I forgot this thing that there is also an additional DC current source flowing at this node. So let's call this node as X, node X, with a node voltage of Vx. So what we are supposed to find out is the DC voltage at the output. Okay, one of the input terminals of the op-amp is at a DC voltage of VCM. Given this information, you are supposed to find the DC voltage at the output. Then you are supposed to find out the impedance looking into this node X. And finally, you have to find out the ratio of V0 by In, which is the transimpedance amplifier's gain. These are the three quantities you are supposed to find. Now I'll start with the DC output voltage and the output impedance Z of S, because those two are much simpler problems. You can solve them by intuitions itself. I will explain in a slightly lengthier manner, but they're very simple. If you have some experience analyzing circuits, you can see they are very simple to arrive at. However, the transimpedance gain requires some KCLs and KVLs. So that I've pushed it towards the end of the lecture. It requires some analysis, which I'll take you through. So first, we'll find out the output DC voltage. So to find the output DC voltage, open circuit independent AC current sources and short circuit independent AC voltage sources. Okay, you have to do that and open circuit all the capacitors. Now, once you do that, this circuit here will reduce to something like this. So the resistor R here will be floating, and I've removed the capacitor here, and the capacitor here also I've removed it, so the input resistor doesn't come into the picture. So this is how the circuit is reduced to. Now this circuit current resistor is floating, so no current flows through the resistor. Now what I'll do is I can quickly, the next step, right, any op-amp circuit, the first thing you have to find out is what kind of feedback is it in. So we can quickly see it is in negative feedback. And what is the negative feedback factor? In fact, it is actually 1 here. So how do you find that? Apply a small signal. I'm applying, remember, it's a small signal DC. It's a DC signal, but it's a very small signal on top of whatever the bias DC is at. So if I apply a small signal Vx, I can remove this remember, I'm using the word small signal, but it is actually VODC plus Vx. Vx is also a DC value, but a small delta V that I'm applying at the output. If I apply that, I can ignore the current source here. It's a fixed current source, so I'm ignoring it. So then the circuit reduces to something like this. You have a total resistance of 2R in series and a floating resistor R here. So if you apply a small signal voltage Vx here, the entire Vx is going to appear here. So it's in unity feedback mode. So it's in very strong unity feedback mode. So therefore, the op-amp is in negative feedback. Now you can apply all the results that you know. The first result is that the inverting and non-inverting terminals will track each other. So the DC voltage at the positive terminal is Vm. This node will also come to VCM. Okay, it's at VCM. Then the inverting terminal will also come to VCM. And since the current through the resistor is 0, the other terminal of the resistor will also be at VCM. Okay. Now we know the current through the resistor is 0 and the input current flowing into the op-amp is also 0. So therefore the current through the resistor here is also 0. So this current is 0. So which means there is no voltage drop across the resistor. So therefore, the node voltage Vx will be simply VCM itself. The node voltage at this point will simply be VCM. Now, to find the output DC, we have to see, we also have a DC current source here. So we need to see how much of it is flowing into the resistor. Okay, you are injecting a DC current source into this node X. So we have to see how much of it splits into this resistor and this resistor. We just saw that the current flowing through this half of the resistor is 0, right? Because that's ensured by negative feedback. This node is at VCM and no current flows into the opamp and the resistor here. So therefore this resistor current is 0. So which means this entire VCM by R flows through this resistor. So the voltage drop across this resistor will simply be VCM itself. So this voltage will be VCM and the node voltage Vx is already at VCM. So now immediately we can see that the output voltage, let's call it V0 DC, will simply be, I'm using this notation, I'll maintain it throughout this lecture. So VR represents the voltage across the resistor. The negative voltage, negative terminal is connected to the output. So that's how I'm using the notation. And if Vx is the node voltage at node X, then the output voltage is simply given by minus VR plus Vx. So that comes from KVL. Okay. So directly substitute, VR is VCM, so you get Vx is VCM. So you get minus VR plus VCM is 0. Or you don't have to do the analysis if you analyzed sufficient number of circuits, you can directly see that if this node voltage is at VCM and you're dropping VCM across the resistor, then this output voltage comes to 0, right? So that's what I've drawn here. I've just cut this portion of the circuit and showed it here. So this is node Vx, this is at VCM, and the entire VCM is dropping across the resistor. I don't care what the load here is, okay? That output voltage comes to 0 volts. The DC voltage comes to 0 volts. So output DC is just 0 volts. So that's what I've shown here. I've shown all the DC voltages across different resistors here in the circuit. The next part of the circuit is to find out the AC impedance looking at the node X. So again, when we are doing AC analysis, what we will do is that we will remove all the independent current sources, short circuit DC sources. So that's what I've done here. So I've short circuited VCM, I've removed the current source at node X, it's a DC current source, I've removed it, okay? And at the input, I had input current source IN, I've open circuited it, and I'm left with a network that looks something like this. R, C in, R and C. This is the network here. So for the analysis sake, I'll assume this entire network as an impedance Z. Okay, I can further reduce it based on the I have given this assumption C in is much greater than C. I have given this assumption, but let's not worry about it right now. This entire network, I'm going to call it Z. Now, even if you notice this circuit here, there is a strong negative feedback. Again, even though there is a capacitor here, there is still negative feedback present in the circuit. Okay, and this opamp is ideal opamp. So there is a strong negative feedback. Therefore, I can assume if this node is at AC ground, this node negative terminal, the negative input will also be at 0 AC volts. So therefore, whatever be this impedance Z is, the current flowing through this impedance will be 0, right? Because the voltage across it is 0. Both the terminals are 0 volts. So the current flowing through this guy is 0. I might as well remove it, or I can simply keep it at 0 volts. Okay, I can, because the current flowing through this resistor is 0, I'll remove it. So now the circuit becomes something like this. Okay, now I'm supposed to find out, now the next goal is supposed to find out what is the impedance looking at this node here. Okay, so I've removed this impedance because no current is flowing through that, and this node is at 0 volts. Now if you look at the circuit here, how do I find impedance? Since remember, I can't drive this node with a voltage source, and find the current. Why I can't do that? Because I will be interfering with the negative feedback. I want to capture the feedback in action. Okay, so I can't drive this node with a voltage source. If I drive it with a voltage source, I'm killing the op-amp feedback action, right? So if I'm driving this node with a voltage source, let's say I'm driving it with some V test and I'm trying to measure the current, then what am I doing? I'm forcing this node to be at AC ground. So the op-amp has no reaction to it. So by the time you apply any test Vx here, so this node voltage is always fixed at Vt. So I can't do that. I want to capture the op-amp's negative feedback in action. So how do I find impedance then? I inject a known current source, let's call it IAC, and then I'll measure the voltage developed across it at that node Vx. So then I'll then take the ratio of Vx upon IAC to compute the impedance Zx of S. So I'm injecting a current IAC into this node right now. Okay. So now we have already seen this node is at 0 and no current is flowing into this node because on this side the current is 0 and input of the op-amp is also the current is 0 and therefore the current flowing through the resistor is also 0. So therefore the voltage at this node will be 0. Whatever be this R and C values are, the voltage at this node will come to 0 volts. So therefore I have applied a finite current and the node voltage Vx is given by IAC times Zx of S. I applied a finite current, the output Vx is 0, therefore the impedance Zx of S is also 0. The impedance looking at this node is actually 0. Okay, so that's it. So that's why I said this just requires intuition. You don't need to do a very complex analysis for this. Now finally, we come to the third part of the question, which is you're supposed to find out the transimpedance amplifier's gain, okay, which is V0 by In. So here I've removed all the DC sources, I've short circuited the VCM, I've made it 0, and I've open circuited this current source, DC current source is removed, and this part of the network, okay, so there is In and a capacitor Cin coupling it to the op-amp circuit. So this is the circuit. So to analyze this, what I'll do right now is I'll try to find out this node voltage. Let me call this as Vin. Once I find out Vin, then I'll analyze this op-amp separately. So I'll first find out this node voltage in terms of In. Once I know that, then I'll try to find out V0 by Vin. And then I'll multiply it with Vin by In. Right? So this is what I'll first find out, what is Vin in terms of In, and then I'll find this gain provided by this amplifier. So that's it. The only problem here is I have a slightly complex network here. How do I find out what is the voltage Vin in an intuitive way? So first step, the impedance seen at this node here with the resistor here is simply R. So this I think we have already analyzed. If you have an op-amp in negative feedback and you're looking, the impedance looking at this input at the inverting terminal will always be 0, right? So because this op-amp is in negative feedback, we just saw that there is a feedback network connecting back to the negative terminal. So there is negative feedback in the op-amp circuit. So therefore these two terminals will track each other. So this node comes to 0, we called it virtual ground, and which means whatever current you inject into this node, the voltage will always remain at 0 volts. So which means the impedance seen at this node will be 0. So therefore the impedance seen at through the resistor will be R. So at the input port, I'm drawing the input port. The circuit reduces to something like this. You have a current source In, a resistor R, and you have another network R and C in parallel. Okay, there is a capacitance C in series with this. Now in the question I said assume Cin to be much greater than C. Okay, so you can do the analysis. I'll probably very briefly explain it now, but you can do it. If you make that assumption for frequencies greater than 1 by R Cin, this capacitor can be assumed as a short circuit, which is high frequencies. Okay, for higher frequencies, I can assume that this capacitor will act like a short circuit, because if you see at DC, the capacitor is open circuited. So therefore, the transimpedance gain will be zero. No current flows into this amplifier, so therefore the transimpedance gain will be zero. So generally, whenever you AC couple, we are interested in the gain of the amplifier after the AC coupling frequency. Okay, that's why I had given this assumption Cin is much greater than C. So which means for all those frequencies of interest, I can assume Cin to be a short circuit. Okay, and I'll probably explain it very briefly how I made that assumption. If you look at this input port, you have a current source feeding into a resistance R, and then you have the input capacitance. Okay, so this is the circuit, equivalent circuit. I can just redraw. I've just redrawn this circuit this way. All I'm trying to say is that the impedance offered by Cin will be much smaller compared to the impedance of R and C in parallel. And you can easily show, I've already discussed enough first order circuits for you to draw the impedances. If you see the impedance of R and C in parallel will be like this: R at DC, and after the pole 1 by RC, it will roll off. This value is R by 1 plus SRC. And the impedance of 1 by SC will look something like this. Okay, all I'm trying to do is finding out what is the frequency at which 1 by SC becomes smaller than this impedance. Okay, just go through that. If you don't follow this, it's fine, ignore that. All I'm trying to say is you have AC coupled the signal. We are therefore interested in frequencies after the AC coupling frequency, which is the frequencies where I can assume Cin is nearly a short circuit. And I've given that condition Cin is much greater than C. It just satisfies that. Okay, I've shown this in the figure here. At what frequency 1 by R Cin, after that frequency, you can assume this capacitance to be a short circuit, because the capacitive impedance becomes much smaller compared to this impedance. So these two are in series. So I can assume the larger impedance will start dominating the overall impedance. So therefore this R and C in parallel will dominate Cin. Okay, so or you can just ignore all that. If you have not done enough RC circuit analysis, you can just assume a AC coupled Cin, and the frequencies of interest for an amplifier designer will be when this AC coupling frequency is crossed, or we are looking at frequencies after the AC coupling frequency, which means the capacitance can be assumed as short circuit in those range of frequencies. So that's what I've done. So at the input port, the circuit reduces to R, the input resistance, in parallel with an parallel RC network. So totally it reduces to a network of R by 2, R and R in parallel. So you get R by 2. That comes in parallel with a capacitance C. So the equivalent resistance will be R by 1 plus SR. So in this case, R is replaced by R by 2. You get R by 2 by 1 plus SRC by 2 times minus In, because I've shown the polarity of In to be flowing away from this node. So I've called this node as Vin right now. Okay. So what you get Vn is minus In times R by 2 by 1 plus SRC by 2. Now that I know Vn, I'll try to find out V0 by Vn, and then I'll plug in this expression to get the final answer. So now I'll analyze this circuit. So I've applied Vn at this node, right? So we are at this node here. I've just found out the voltage at this node. We are at this node here. Now we are supposed to find out the output voltage in terms of Vn. So to do that, this is a circuit. Again, the negative feedback is not a conventional negative feedback. It's a T network. So you have to do some KCLs and KVLs to arrive at the final answer. I'll leave that part to you. Probably you can just freeze the screen and look at the expressions here. But I'll quickly do the analysis. Okay. So if you apply Vi here, so you'll have a current Vn by R flowing through the resistor, and that current will flow through this resistor here. So this node voltage is at 0 volts. That is by negative feedback, it's at 0. So, and the voltage across the resistor is Vn, So because you have a current V in by R flowing in this direction, so the voltage across the resistor will be plus V in, and this node voltage Vx, you can write KVL at this node and directly see that that node will be minus V in, right? It's the voltage across the resistor plus this, so this is at 0 volts and you are dropping plus V in volts. So the node voltage Vx will come to minus V in, 0 minus V in, so it will be minus V in. So Vx comes to minus V in. Now once you know this node voltage, then you can apply KCL at this node and estimate what is the current flowing through the resistor R. Okay, so I'll quickly, you can see that the current flowing through the capacitor will be Vx into SC plus the current flowing. Remember, this current is flowing away from the capacitor, and the current flowing into this node. So you can just apply Kirchhoff's current law on this node. So I'll just group incoming currents equal to outgoing currents. So the outgoing current here is IR and the current through the capacitor. So I'll write IR here, which is what I've shown here. IR here is minus Vx into SC. That's the current going through the capacitor, and plus V in by R. So this is the current flowing through the resistor. So solve that and you can just find out the output voltage to be V in into 2 plus SRC, or I can write it as minus V in into 1 plus SRC by 2. Okay, so and then plug in V in as I in here. Finally, you end up getting a result of V naught by I in as R. Okay, you can just freeze the screen and take it. But we can also solve this problem in a more intuitive way. That is by, if you know, most of you must have done a basic electrical sciences course. Whenever you see a T network, you try to convert the T network to a pi network. So that is something we are used to. We are used to this idea that if you have an impedance Z in the negative feedback path, that we know some standard results and how to analyze that. That is something we are already aware of, right? So we don't have to, we can just use some ready-made results and we can avoid all these extensive calculations. So then all I need to do is take this network, this is a T network, convert it to an equivalent pi network. So that's what I'm going to do. Convert it to an equivalent pi network. And what I'm interested in is what is the network in the what is the impedance between input and output terminals. That is the impedance that will decide my gain, because if I convert it to a pi network, I'm going to put, let's call this impedance as Z1 and this impedance as Z2, and the impedance here between the input and output as Z3. That's how it will be converted to. I really don't care what Z1 and Z2 are, because Z1 is at the inverting terminal. Since this is a virtual ground, no current flows through Z1, so I can ignore Z1. Okay, and Z2 is at the output node. Again, for an opamp, ideal opamp, the output resistance is 0. So whatever Z2 you connect here, the output voltage will be determined by the feedback network. It is not determined by the load impedance. So we can ignore Z2 as well in the analysis. So all I need to do is find out what is this impedance between input and output terminals, the value of Z3. So if you have an impedance network like this, so there is a standard result. If you have a T network impedance, so let's call Z1, Z2 and Z3, then the impedance looking between these two nodes will be Z1 plus Z2 plus Z1 Z2 by Z3. Okay, this is something you have to know. So again, so all my exams in my university are open book. So meaning you can carry any book you want to. So generally I assume that these results are known. So you can just look into a book and you'll find this result. Okay, it's you can derive it as well, but we can use this result. If you use this result, the problem becomes very simple. So now you have R plus, so you get R plus R plus R1, I mean Z1, Z2 is R into R square by 1 by SC. So you get R square into SC. So you end up getting an inductive impedance using a capacitor, because this part increases with frequency. So you end up getting an inductive impedance. So you get 2R when series with SCR square. The value of the inductor will be CR square. So this is one way of emulating an inductance, using a T network. You can do that. So now if you see, I'll substitute this circuit here. As I said, the impedance is Z1. I mean, we can find what Z1 and Z2 are, but they don't matter in the pi network. They don't determine the gain. So I'm left with a circuit that looks like this. You have R here and you have 2R plus SCR square. So this impedance is simply, if I take 2R common outside, I'll be getting 2R plus 1 plus SCR by 2. So the gain of this circuit will simply be, you divide this by R with a minus sign, minus of Z2 by Z1, the feedback network impedance I'm calling it, or let me call ZF as the feedback network, divided by Z input, which is R here. So you get minus 2 into 1 plus SRC by 2. Now that you know this gain, you can substitute the input gain. From input again, you know what Vin is in terms of In. You substitute that, you will get the expression V naught equals In times R, and you get the transimpedance amplifier's gain as R. So all I'm trying to say is that in the circuit, if you see, we introduce a pole at the input. Okay, there is a pole that gets introduced at the input. That pole gets cancelled by the zero in the feedback network. So this circuit, you can look at it like a wide bandwidth. You can look at it like a wide bandwidth transimpedance amplifier, right? There was some input pole. I'm just using an opamp to cancel that input pole. That's it. An opamp and some T network based circuit to cancel that input pole. Okay, so that's all I'm doing. So that's why I thought this is an interesting circuit to share. So that's it. So finally, the three answers: the output DC voltage is VCM, the input impedance ZX of S, the input at node X ZX of S is 0, and the transimpedance amplifier's gain, TIA gain, is just R. Okay, so if I made any calculation mistakes, just let me know. Thank you.